It's a pleasure to be here to tell you about what we're doing in our fuel cell work and how that connects to storage. So the idea is that we can go back and forth between fuel and electricity. Okay, so in terms of how we put this in terms of our sustainable energy cycle, the idea with a pointer that doesn't point, let's use the pointer that does point, also barely. Well, we are now talking about the recognition that wind and solar electricity are becoming quite cost effective. We've talked about different ways of doing the storage. And if you can do the storage here in a reversible electrochemical cell, this would be something that would operate very much like a battery in the sense that you can use it for storage and then subsequently use it for electricity delivery. But it can, similar to a flow battery, it can decouple the size of the storage tank and the size of the device that's doing the electrochemical conversion. But in contrast even to a flow battery, what it can do is produce hydrogen that you could conceivably use for portable applications or any other needs. So just to remind you then how a fuel cell works, the first part of what I'll tell you about is in our fuel cell work, is that if we have a material here which is a proton conducting electrolyte, we have an anode and a cathode on either side, we bring hydrogen and oxygen to either side. These are our reactants that would like to get together and lower their Gibbs energy and release the energy for us to use. They're in our favor, I guess. Hydrogen and oxygen there, but they are separated by this electrolyte. So as a consequence, for the reaction to proceed, we have to have this electrochemical step that allows the hydrogen to turn into protons and electrons. The electrons go through the exterior circuit, the protons through the electrolyte, and then on the cathode side, we complete the reaction where the oxygen, the protons, and the electrons come together and give us water as our product. So this is the overall typical fuel cell principle of operation. And we characterize the fuel cell by what's called this polarization curve, where we look at the voltage as a function of current density. So under open circuit conditions where we're not drawing any current out of our system, we have a voltage that's essentially determined by the thermodynamics of our system. And so that'll be on the order of 1 or a little over 1 volt, depending on the temperature that we're operating. And then the voltage may often, this open circuit voltage may often be lower than the Nernst voltage for a number of reasons, even under open circuit, because of perhaps leaks, electronic leaks, or other sorts of leaks through our membrane itself. And if you're working at high temperatures, as my lab does, the students are always very sad because they have leaks in their seals, and you're not learning much about your material yet. But that once you address that, then you start to draw the current, and now the voltage decreases because of things like the finite reaction kinetics. That's usually what we call our overpotential in here. And then as we start to draw more current, we start to see the impact of the ohmic resistance through the electrolyte, and very high current densities, we start to see mass transfer resistance. So the power density that we get out of this fuel cell is established by simply taking the voltage multiplied by the current density. So we get a power density curve that has this peak value at intermediate conditions. And typically we operate our fuel cells at around 0.7 volts, which is around here, to give us a balance between the efficiency, which is high when the voltage is high, and the power output, which is high when we're close to this peak power. Okay, so, and fuel cells, if you consider them and compare them to combustion and so on, the reason they're very exciting is because of the high efficiency. And efficiency that is independent of size and is also gives you zero emissions, so things like acid rain producing, sulfuric acid and nitrous acids and so on. And again, as I mentioned, it's very much operable on hydrogen. So the grid average here is maybe a little over 30% efficiency, and a fuel cell, if you do it, especially the high temperature fuel cells, if you do that with some sort of combined cycle where you use the waste heat, then you can, in principle, get to extremely high efficiency. So this is why there's continues to be excitement in fuel cells. And let me just show you that this technology is starting to make it into the marketplace. And so this is the sales of fuel cells that are shipped and implemented worldwide. Up until a few years ago, this was primarily in stationary power. In the last couple of years, that has shifted towards transportation, and much of that transportation is, in fact, in bus fuel cells in China. So this is very interesting because most of the manufacturers, this is a US company, Canadian company, US company, and German company. So as we run into trade wars, I think this company might be the best position to take advantage of this market. In any case, so there are many different types of fuel cells. So I mentioned that these are transportation versus stationary power fuel cells. So they're essentially differentiated by the temperature at which they operate. Stationary fuel cells typically operate at these rather high temperatures, and they incorporate an electrolyte, which is a phosphoric acid electrolyte, molten carbonate electrolyte, or a solid oxide electrolyte, and then FC is just for fuel cell. And that establishes the temperature because that's the temperature that you need in order to get the ions to move through that electrolyte. And the two lower temperature systems, the one that is primarily used in automotive applications is the polymer electrolyte membrane, and you've heard of that also in the Nafion-based systems, which is often called a proton exchange membrane fuel cell, but in fact I would call it a hydronium ion exchange fuel cell. And then a little bit higher temperature is the alkali fuel cells that have been used very much, for example, in space applications. So as you go to higher temperatures, you typically get increased fuel flexibility and efficiency. This is not an inherent thermodynamic efficiency from high temperature, but a catalytic efficiency, because catalysis generally proceeds more readily at high temperature, and so that provides you with that increase in efficiency. On the other hand, you want to go to lower temperature for easy thermal cycling, and so that's why portable applications don't usually rely on a fuel cell that's operating at 800 degrees Celsius or so. But you'd like to get some of the advantages of both systems, because by the time you're at these temperatures, you actually don't need a precious metal catalyst anymore. Phosphoric acid fuel cells do use a precious metal catalyst, but by the time you're at the molten carbonate or solid oxide fuel cells, you're not using precious metals anymore, so that's an advantage. Alkali fuel cells also don't use precious metals, but that has to do with the easy oxidation reactions associated with the different reaction pathways here. All right, so we don't like these systems, though, because they have corrosive liquids. At least my background is in material science, so I like solid materials that we can use for engineering purposes. And so we have this target regime where we'd like to use a solid electrolyte. And there are a number of materials that have high conductivity at this intermediate temperature range. So if we want to be at this between 250 and maybe 550 C, there are these three different materials that we use in my laboratory, but I'm going to talk to you primarily about this oxide here, which is an oxide which we can make into a proton conductor by modifying the chemistry such that it has some oxygen vacancies in it, and then expose it to high humidity, in which case the vacancies are filled up by hydroxyl groups. A second proton attaches to a second oxygen atom in the structure, and then these protons at these hydroxyl groups can jump from one site to the next, and that gives us good proton conductivity. So it compares here with some of the polymers that are, the highest temperature capability polymers out here. Okay, so now why would we want a fuel cell that's based on a proton conductor as opposed to the other high temperature systems which are oxygen ion conducting? Well, it's been recognized, first of all, I already pointed out to you that the temperature is lower than in the case of the oxygen ion conducting systems, which is around 800 degrees Celsius. And that is not so low, and so because it's still high enough that the catalysis rates are high, and we have good impurity tolerance then, so we don't have to clean up our fuel as much as we would, for example, in a PEM fuel cell. Significantly in terms of an operation perspective is that if we're supplying hydrogen here, we can recycle this fuel if it's not completely utilized without having to worry about dilution effects, whereas in the oxygen ion conducting system, the fuel is diluted, so recycling becomes difficult. Okay, so this is an operational condition that compares the two high temperature systems. Okay. Now, I showed you that the ionic conductivity of these proton-conducting electrolytes is quite high, so you might imagine that the fuel cell power outputs from these systems would be comparable to what has been shown for the oxygen-ion conducting systems. They're very similar in many ways. And when we took a look in about 2014, when we got started with an ARPA-E project, this was at the time we were putting the proposal together, said, look, you know, this is really quite intriguing. If we look at the peak power densities from these fuel cell systems that use protonic ceramic electrolytes, they're nowhere close to what the oxygen-ion conducting system had done 10 years ago. So this is an example from my laboratory where we had a nice result. And numbers of laboratories have reproduced this result. So the oxygen-ion conducting systems are doing quite well at this temperature, but the proton conducting systems were not doing well. And so this was saying there's low power output despite this high electrolyte conductivity. In addition, these materials here we knew were a little bit reactive with CO2 and steam, so that was also a detrimental feature of these electrolyte systems. So we wanted to understand why they weren't doing as well as they should, and could we come up with a better electrolyte. And so this is a bit of an eye chart here, but what I want to point out to you is that all of those systems that had low power densities, what we could see is that what's the ohmic contribution, so that what should be due to the electrolyte, was much higher than what you expected. So the measured value was, many times an order of magnitude higher than what you expect from the electrolyte. So either the electrolyte itself was, not good in some way, or there was some contact resistance, or somehow these very complex chemistries were having difficulty in terms of the fabrication, or perhaps there was poisoning from this nickel that was in the anode component that was poisoning the electrolyte. So we said, we need to really understand this and both create better electrolytes and establish, I'll show you the issues of the contact resistance. So coming up with a better electrolyte, we looked at these materials. I mentioned the dope barium zirconate. This is a perovskite, and there's a dope barium cerate, and there's trade-offs between these two. And so the straightforward thing to do is to say, let's look at intermediates. But as we do that, let's think about what kind of dopant we would use. So these are the good choices of dopants. So we looked at these intermediates using these materials as dopants. And you put all that together, and we developed then some new electrolytes that had somewhat higher conductivity than this hard-to-process material. And we did establish then that it's not reactive with CO2 because we put it in a CO2 environment here at high temperature, and there's no mass gain. So we have a nice electrolyte. We can move forward. Okay. So now we want to make a better cathode. And we have the idea here that if you look at the oxygen-ion conducting systems, what people do is, and what we've done, is to try to develop oxygen electrocatalysts that are active over the entire area and not limited to reaction sites right here, so we're going to eliminate that. This is always the concern about using, allowing your slides to be put on a different computer, but this is supposed to be an arrow, not, I don't know what country's currency that is, but anyway. Pardon? It's a EU? EU? Okay. A euro, yes, that I should know. Okay, so, and I could use some European funding, so that would be good. We'd like to develop an analogous system where we have a mixed proton-electron conductor that allows us to have the electrochemical reaction occur over the entire surface of this catalyst material. And so we're allowing protons to move through. This has a good electronic conductivity that lets the current get to the reaction site, and this whole surface is catalytically active. That's the idea. The challenge is that developing this sort of material has been just not really proceeded. So again, we need more money to be able to do that. So, so instead, if we look at these traditional oxide electrocatalysts, we know they're oxygen-ion conducting. They would be actually bad news to use because you would start to evolve water right at the interface between the electrolyte and the oxide. That would be bad news. You'd start to delaminate. But there's now evidence that these materials are what are called triple conductors. So in fact, they allow all three ions to move through. And in fact, because the protons move through quickly enough, you get electrochemical reaction on the surface. The electrons move to the reaction site quickly and all of that. So this is a great system to be able to develop new cathodes. So we looked at double perovskites in particular because they had been demonstrated to be very effective with the oxygen ion conducting system, and another example with the proton conducting system. So we use this one. And I'm actually afraid of running out of time. I don't have a watch or my phone, so I'm a little, how am I doing? I unfortunately left my phone in the car, so I have no idea on the time. But all right, so this is our new cathode material that we decided to use for this system. And we first made sure that it was chemically compatible with our electrolyte. And after seeing that, we established that it has a lot of proton uptake, which is useful for getting the species through it. So we could see that the proton concentration is reasonable at the temperatures that we wish to operate. And just to show you that it is also less than the total oxygen content, so we're not overfilling the sites. And we did an experiment where we wanted to establish that, in fact, the entire surface is electrochemically active. And we did that by micropatterning a number of these microdot electrodes on top of the proton conducting electrolyte, measured the electrochemical reaction resistance here, and observed that this scales with area. And that demonstrates to us that this is active over the entire surface. Okay, so that may seem like a detail to you, but it turns out that this is very important for us, the fact that this entire surface is active and that the protons can make their way through. That means that we have a lot of active sites available, that we want to maintain high surface area when we actually make the electrode, and we can ideally access all of those sites. So we went ahead and made the fuel cell out of this. Here's it's a relatively sort of traditional ceramics processing that we've done here. So this is not microfabrication. This is a colloidal deposition of an electrolyte on top of a composite electrode, and then colloidal deposition of the cathode. And we have high surface area of this cathode material. As I described to you, we have electrochemical reactions over the entire surface area here, so we don't have to worry about whether the electrons and protons can get there, because this material transports the species of interest to its surface, so that it means that all of that surface is available. And then because we were very concerned about the good contact resistance, or good contact, so we would not have high contact resistance, we deposited a very thin film of this same cathode material directly on the electrolyte so that the electrons and the protons could get through to this site and eliminate the contact resistance that we interpreted was the cause of the poor performance of all the prior literature fuel cells. Now, if this material were not proton permeable, this would be an extremely bad idea, which is why we took the effort to demonstrate that, in fact, the protons can make their way through, the electrons can get there, and the protons can also make their way through and get to all of this material for the electrochemical reaction to proceed. Okay, so now we have that, and we compare our, start making our polarization curves, and we get, I'll put this in the context of the prior literature in a moment, but we have, we're drawing amps per centimeter squared here, just to put this in the context of some of the other numbers that you've heard. And this is at now moderate temperatures, so we're not at 800, 1,000 degrees Celsius, which is the case for the oxygen ion conducting systems. And we did show that having this thin layer is important for increasing the power density. So our peak power density, so that's the point right here, is increased by having this thin PLD layer. And we could also see that it was impacting that ohmic resistance and therefore what we view as the contact resistance. So that's where we're seeing that significant benefit. And we make sure to do multiple samples. We're not chemists who are stuck with just a few milligrams, as was mentioned earlier. We can make large-scale samples and do this multiple times and see it's quite reproducible. Okay, so let me now show you then in 2018, a couple of other nice results had come out, but here's our fuel cell, and we're using a stable electrolyte, so that's been a lot of fun. So that's our record performance there. And then we also, of course, measured stability, and it lasts for a very long time. And that's important because we have that 100 nanometer thin layer, so we wanted to ensure that that was nice and stable as well. Okay, so now we're doing better than the oxygen ion conductors are doing. So now let's go back to the notion of the storage, which is why we're here. So let's go back to thinking about making this reversible. So what does it take to make it reversible, and why are we doing this? So, you know, I think many people in this room recognize now this, you know, solar electricity prices are coming down, wind electricity prices are coming down. We need to think about what to do with that electricity. Okay, so if we're going to use our electrochemical system for making hydrogen by electrolysis, again, we're going to compare the situation with the oxygen ion conducting system because we're operating at high temperature. That's our competition. Let me say that in comparison to low temperature system, there's an inherent benefit because the voltages are lower at high temperature. So that can be a real benefit for just the system operation. But that's efficiency in these contexts. You have to take the whole picture into account. But in any case, the voltages are inherently lower that you need to operate at. But if I compare these two systems, there's some intriguing differences. First of all, this electrode, this is the fuel electrode, where I showed you we have nickel as the electrocatalyst, and this whole thing is our thick electrode because it is the piece that is providing the mechanical support to this 20 or so micron thin membrane. Okay? And so this is a lot of nickel that's here, and we are able to operate this system where we are basically removing hydrogen from this nickel side. We are supplying steam to the mixed conducting oxide electrode, which was our, I'll just call it air electrode because it's operating as an anode in the electrolysis mode. So our air electrode is the one that's being exposed to steam. So in this case, this material is very happy. It's an oxide. It has no problem with seeing a whole lot of steam. In the case if you were using an oxygen ion conductor, you have all this nickel, which is still serving as a support, and if you supply it with steam, it just is not very happy. And so degradation in this system is quite severe. There are other aspects here, so that when the fuel that you produce here, it's just dry hydrogen, essentially, whereas here it is generated along with the unreacted steam, so you may have to do a separation step later. That's not so costly because removing steam is not so hard, but it is an extra step. And there are issues also, let me describe this point, that if you're bringing steam through this thin electrolyte, we don't run into mass diffusion limitations in the way that there are mass diffusion limitations here. So that ties into the fact that we don't want to have a lot of steam here, but we have to have a lot of steam because the steam has got to diffuse through this rather thick layer, which is maybe a few millimeters or so in thickness, where here the steam is only going through something which is like 20 microns. So we have to have a high concentration so that we don't have a mass diffusion loss, yet we have nickel that we're going to oxidize, and that becomes a problem. Now, the hydrogen evolution happens here, and hydrogen, those overpotentials are typically quite small, so you don't drive bubble formation and therefore delamination, whereas in the case of oxygen evolution, overpotentials tend to be high and become enough to create bubbles and cracks, and that becomes a problem for this system. So there's a lot of reasons why we use our advantageous for using the proton conducting ceramic for the electrolysis. And so experimentally, it's very easy for us just to change the direction of our current. This is a straightforward experiment, and so we did that. We did one thing, which was put high concentration of hydrogen here, and that's just sort of historically people do that because you want to think about pressurizing the hydrogen to be able to put it into some sort of tank. And so we're operating in electrolysis mode and fuel cell mode, and we have good stability. And again, if we compare these numbers to what we heard perhaps earlier, these are many amps per centimeter squared, and what's considered the neutral voltage, which is around 1.3 volts, we have many amps per centimeter squared as the polarization that we're getting out of this. So unfortunately, science reviewers decided this was too good to be true, despite the fact that I'm extremely careful. So if you were one of those reviewers, we are really careful. And in any case, it works well, and it lasts a long time. Again, we can't use our stations for very much longer than several hundreds of hours, but we just took this out because we were tired and had to put another station in. Now, there is a challenge. And that is that there is a little bit of electronic leakage through this electrolyte. And it's not very much, so we have 97% transference number for protons, so maybe about 2 or 3% transference numbers of electrons. And you think, okay, that's not so bad. But that's true in the reducing atmospheres. When you go to more oxidizing atmospheres, now the transference number of protons decreases. It's not terrible to have it be somewhat oxygen ion conducting, but it is a problem if it is electronically conducting, because that means that you're just losing some of your current towards just making heat, basically. And so it's also quite difficult to measure the Faradaic efficiency. You might think, well, just put a detector and measure how much hydrogen you're producing. That would be the obvious answer. The reason that it's difficult is that we're typically supplying this very high amount of hydrogen to see how much additional hydrogen we could make, and as I said, pump up some sort of tank so that we could have high-pressure hydrogen. So now if you're producing a small amount of hydrogen from this 3% steam, that's hard to detect over a large background signal. You can detect the oxygen that's produced on this side, and that's a little bit easier because it's not quite a high background, but it's still a high background. So you'd say, well, let me move towards having, for this experiment, let me reduce the hydrogen amount that I'm supplying to my fuel electrode so that I can measure it, so I can measure the hydrogen that's being produced from the electrolysis. The challenge there is that, that's good, that works, but you're going to underestimate the Faradaic efficiency because now you've moved into the regime where the electrolyte is actually a little bit more electronically conducting. So you're going to make your numbers look worse than they would be if you were in this sort of more operational condition. On the other hand, you say, let me change this, what I'm supplying to my air electrode, and move into something that is a little less oxidizing so that I can actually see the oxygen that's being produced. Okay, so that's good. I'm going to be able to measure over a small background, maybe negligible background, but now I'm going to overestimate the Faradaic efficiency because I've shifted my electrolyte into a regime where the electronic conductivity is much, much lower. So that is inherently a challenge, and I can say that when we looked at the literature to try to compare our numbers, I'm pretty sure that everyone's done this wrong. Not that many people have measured it. Most people would just assume that because this is an oxide electrolyte, this is 100% Faradaic efficiency, there's really nothing else that can happen. But that small percent of electronic conductivity is probably not a big deal, but in fact it is a big deal. And the incorrect assumption that happens is that at zero current, there's zero fuel production. So you might say, well, that makes sense. That's a very reasonable assumption. But in fact, at zero current, we have negative fuel production because we're just leaking a little bit of hydrogen across the membrane. Okay, so we do some electrochemical impedance spectroscopy to measure so we model our system. Here's a little bit of this electronic leakage and so on. We do now are able to calibrate what we measure at our mass spec to be able to say how much the hydrogen production actually is. And again, at open circuit, we see that there's a negative value. Again, this is calibrated through the impedance measurements. And then we can estimate the Faradaic efficiency. And now what's very nice, we can calculate sort of what we expect based on an electrical model. And our measured Faradaic efficiencies here are actually quite reasonable, around 70% or so. And they increase when we go to lower temperature, as you expect, because you have less electronic leakage at high temperatures. Okay, so now if we put this together, here's our electricity generation. In this case, electronic leakage is not a problem because of you're operating in forward. I can have a conversation with you in the coffee break to explain why electronic leakage does not impact the fuel cell results, but it can be problematic for the hydrogen production. We're at 70% Faradaic efficiency at these lower temperatures. And again, if we compare the current densities to prior work that's all been done with oxygen ion conductors, you can see that our current densities are substantially higher. And in these cases, again, no real measurements of Faradaic efficiency. So we can see that this is really moving this forward. And we have very good ideas in terms of how you might eliminate that small amount of electronic leakage, which again is just a few percent, but we have good ideas on how to do that so that you could really bring this to the next stage. Okay, so with that, I want to thank the students and postdocs who've done the work, Suyuk Choi, who's now back in Korea and with his own faculty position, Chris Kacharzik, who's left academia and gone into data science, because that's where all the excitement is nowadays, and Tim Davenport, who's now at UTRC, and we actually continue to collaborate with that group, collaborators at University of Maryland, and my entire research group. And I like to show this picture because we are at the beach, and I go to the beach much more in Evanston than I ever did in Pasadena. So, and thank you for your attention.